Good afternoon, everyone. Welcome to Flip Lectures in Chemistry. Today, we will be talking about an important foundation in chemical reactions. In most chemical reactions, example is after combustion, we might wonder where the forms of matter are. Though the forms of matter are no longer present in its original form as they disappear after the reaction, all of the mass of the forms of matter are still present, but they are already in different forms. This condition was first explained by the French chemist Antoine Lavoisier. According to Antoine Lavoisier, no new matter is created nor destroyed in this planet. Thus, in any chemical reaction, matter cannot be created nor destroyed. He also added that the total amount of mass in planet Earth remains constant, and it is merely changing from one form to another form. This is perhaps one of the reasons why Earth is considered a closed system, but we'll talk more about this in our class tomorrow. Going back to combustion earlier, the forms of matter involved in the reaction did not disappear after all. For example, when combustion started, oxygen gas reacted with a natural gas, specifically methane, to produce water vapor and carbon dioxide gas. And if you mass the reactants oxygen and methane, it would equal the mass of the products water and carbon dioxide. And we can remember the law of conservation of mass with this. We will further discuss this tomorrow. All chemical reactions are represented by a chemical equation. And in a chemical equation, we have the reactants that appear on the left side of the equation. Aside from the reactants, we also have the products. The products are the ones that appear on the right side of the equation. The states of the reactants and products are also written in parentheses to the right of each compound to tell us their forms. For example, we have G, which is for gas, for example, corresponding to the given form of matter, which is methane. It also applies the same for the case of oxygen, carbon dioxide, and water vapor. Since the law of conservation of mass applies to all reactions on planet Earth, all equations must be balanced. And to balance chemical equations, coefficients are actually inserted to balance these equations. Subscripts and coefficients give different information. For example, for the case of subscripts, they tell the number of atoms of each element in a molecule. So for example, given the chemical formula H2O, this means that we have one molecule of water. So aside from that, the subscripts actually tell us the composition of the chemical formula of H2O. This means that H2O has 2 atoms of hydrogen and only 1 atom of oxygen. Aside from subscripts, we also have coefficients. Coefficients, on the other hand, tell us the number of molecules. For example, the combination of the atoms of hydrogen and oxygen produces this chemical formula. 2 here is actually the coefficient. This means that we already have 2 molecules of water. Thus, the composition of this chemical formula is now 4 atoms of hydrogen and 2 atoms of oxygen. Since the law of conservation of mass states that no atoms can be created or destroyed in a chemical reaction, so the number of atoms that are present in the reacted side has to balance the number of atoms that are present in the product side. Thus, there is a need for us to balance a chemical equation for any chemical reaction. In balancing a chemical equation, for example, the equation representing the reaction in between methane and oxygen producing carbon dioxide and water vapor. The first step in balancing is to write the formulas of the substances in the chemical equation correctly. So for example, this is the formula for methane, oxygen, carbon dioxide, and H2O in the form of gas. An arrow in a chemical equation represents or separates the reactant from the product, while a plus sign, on the other hand, is the one that tells us or that separates multiple products and reactants in a chemical equation. After writing the correct chemical equation representing the reaction, we count the atoms of these elements or of the elements on each side of the equation. Since the equation or the chemical equation is always divided into two parts, which is the reactant and the product side, we count the number of atoms in the reactant side and then we count the number of atoms on the product side. For example, we have the atoms of carbon, hydrogen, and oxygen involved in this chemical equation. For the reactant side, we have 1 atom of carbon, we also have 4 atoms of hydrogen, and we also have 2 atoms of oxygen. We compare the number of atoms in the reactant side to the number of atoms in the product side. For the product side, we have 1 carbon atom, 2 hydrogen atoms, and we have 2 atoms of oxygen in the carbon dioxide compound, and we also have 1 atom of oxygen in the water compound. Since the equation is not yet balanced, we adjust the coefficients to make the number of atoms equal on both sides. Coefficients, as discussed earlier, are inserted before every symbol or formula to tell the number of molecules. For example, in this equation once again, we have, for example, the coefficient for the number of carbon, hydrogen, and oxygen atoms. For the case of carbon, since both carbon atoms on the product and the reactant side are equal, we move into hydrogen. For the reactant side, hydrogen has 4 atoms. On the other hand, on the product side, we only have 2 atoms. So to make the number of atoms of hydrogen equal on both sides, we add the coefficient 2 or before the formula for water. By adding the coefficient 2 before the formula for water, we already have 2 times 2, and that gives us 4. So 4 is already the number of atoms on both sides. By adding 2 as the coefficient of water, this does not only affect the number of atoms of hydrogen, but also the number of atoms of oxygen. So if the subscript of oxygen is 1, this gives us 2 times 1, and that is equal to 2. And 2 times 2 is equal to 4. Now, we go back to the reactant side. Since the number of oxygen atoms is only 2 for the case of oxygen, to balance the chemical equation, we add the coefficient 2 once again. And by adding the coefficient 2, this gives us 2 times 2, and that is equal to 4. Lastly, if exact coefficients are already added, we check the number of atoms, or we check if the number of atoms are the same on both sides. So for the case of carbon, we have carbon on the reactant side has only 1, carbon here also 1. Balance. We check for the case of hydrogen. Hydrogen on the reactant side has 4, and on the product side, that gives you 2 times 2, that is 4. So we also have a balanced number of atoms for hydrogen. For the case of oxygen, we have 2 as a coefficient and 2 as a subscript, that gives you 4. And on the product side, we have oxygen here, which is already 2, and we also have oxygen atom on this side, also 2. So 2 plus 2, that gives you 4, and by adding coefficients earlier, we come up with a balanced chemical equation satisfying the law of conservation of mass in chemical reactions.